Okay, so if we're reducing matrix, we have these things we call canonical forms, not a term you got to remember, but you might think about what that means. We try to reduce the matrix to the identity, or at least get the identity as far to the left as possible. Now, if the matrix isn't square, then we might not be able to do that. Okay, we might not be able to get to the identity, but you know. And even with a square matrix, we might not be able to get to it. But ideally, if we have a square matrix, we get something that looks like this, right? Okay? And we understand what that is. Or a bunch of ones with zeros here and zeros here. But then the matrix goes on for a while. Okay, with zeros all through here, right? Make sense? Okay. Or we could have a bunch of ones, the matrix stops here, and then there are a bunch of zeros down below that, right? And we've seen forms like that. So we could get, again, an identity up to here, zeros here, zeros here, zeros here. Okay? Of course, in reducing this, in this case, these don't have to be zeros. So I'm going to call those asterisks. Asterisks. Okay? Make sense? Other my pronunciation? Okay? So, we can get any of these forms, right? Okay? And these forms have interpretations, depending whether we're looking at a system of equations or a transformation or whatever. Okay? And I guess another form, I mean, there are many forms, but we could mention this one, then we'll look at a couple of others. We could reduce down here and we get a bunch of asterisks over here and all the way down to here, and we could get a bunch of zeros. Right? Okay. Even if this is a square matrix, we could all of a sudden find that everything else has been eliminated. Okay? Or they got zeros here with asterisks over here. Okay? All those things have interpretations depending on the situation you're looking at. Okay? Or we could have and I'll write out a couple of explicit matrices. Okay. Now if you have this, then this one is going to allow you to get zeros above it, right? Okay. And this one would allow you to get zeros up here. But we're kind of missing something here, right? Okay? Or it could come down to, it's a square matrix, where we have this, right? And any other combination. We could skip as many here as we like before we get to a 1. The rule is every 1 has to be to the right of all those 1s above it. Okay? And that's your basic restriction. Okay? So, what do these things mean in terms of systems? Well, this would mean like your x1 is 0. Okay? Actually, if it's a matrix, I could put a row of asterisks over here. Okay? And then, well, we're not going to talk about every possible case. Okay? I'm just kind of giving you an overview of all the cases, and then we kind of look at them one at a time. If this matrix defines an equation, if it's, this times a column vector equals some known column vector, we're trying to solve it, we can see we're kind of out of luck here, okay? If we want to solve this thing by inverting the matrix at least, okay? Because this matrix isn't going to invert. Why not? Because if it reduces to this, it doesn't reduce to the identity. So among other things, we can't augment the matrix with the identity and reduce the original to the identity to get an inverse, okay? And also, now that we're talking about determinants, what's the determinant of this matrix? 0. You got a row of zeros. Just expand along this row and you find that you got 0, right? Determinant is 0, okay? So it's what you call a singular matrix. And yeah, there are limits to what you can do with that, okay? So let's look at a couple of specific examples.